All right, let's talk about friction just a little bit more because we talked about friction, I would say, kind of in depth right before break. But now we want to go further into the idea of friction here. So if you look here, I got a 500 gram weight, and then you see I have a 200 gram weight. Clearly two different weights. However, these two surfaces are exactly identical, and we're putting them on the same cork surface here. And what I want you to realize is that I can move my objects by moving the surface itself. And so these objects will move back and forth, and essentially, it's not me that's doing the moving, it's the surface right here that has to be pushing these things forward and backwards. And one of the things I want to show you here is if I just pull it, let's say very rapidly, with a large acceleration, what's going to end up happening is that these objects, oh, that didn't quite work, they actually moved. Let me pull it a little bit faster. There you go. Once I pull it too fast, you see that they slip. Now they actually do move a little bit, but they clearly slipped from this point here to this point here. And the motion looked identical for both objects, so this appeared to be kind of independent of mass. So, this happens in a car all the time. If you accelerate too fast, some of the stuff that, you might have on the dashboard or something might end up sliding. If I pull this slowly, I don't get any slippage happening and these things move. And it's not me causing these to move. It's the board right here. The board is what's in contact. The board has to be what's exerting a force. And then when I pull it very quickly, you see that, well, there's got to be a limit to how fast I can pull this, because if I pull it too fast, they end up slipping. So we want to figure out why that is. And this is where we get into friction. Now, usually we say that static friction opposes the motion. But here, it's literally the cause of the motion. So what we're doing here is we've got a surface here, and here's our mass here, and the surface is accelerating forward, which causes our mass to accelerate forward. Now, as I said, if this thing is going to accelerate that way, it's not me doing the application of force to the object. What it is the surface beneath it applying that force. So if we are diagramming out forces here, we have Fg, we have the normal force, and these two things are present, and then we have to have some force here that's going to cause the box itself, or maybe we'll call it the metal weight here, to move to the right based on how I have this perspective drawn here. And so what we're going to do is we're going to have to recognize is that it's a force that's exerted by the surface, it's a contact force, and it's frictional in nature. And we're going to call it F of S max right now, because what we want to do is we want to find out what acceleration we can move to the right with before this thing begins to slip. So when I pull it to the right, what ends up happening is that if it's accelerating, it's going to be friction that's causing the acceleration here. So friction, static friction, is literally the cause of acceleration. Now, a lot of people go, I thought it prevented motion. And we were kind of very careful to point out that, well, it does, but it prevents motion between these two surfaces here. So static friction is going to hold it in place stationary on this surface while the surface moves to the right. So static friction is going to be the cause of our acceleration. And it doesn't look like a complicated problem from a force diagram perspective. The y direction, there is no motion. So I expect those forces to be balanced. Sigma F in the y direction is composed of N and the force of gravity. And we get that same old normal force equal to force of gravity that we see time and time again. The x direction is actually what's a little more interesting here. Sigma F in the x direction, we are accelerating that way. And the only horizontal force is the force of static friction. And so we're going to write F of S max here because we want to know, well, how fast can this thing accelerate? Keep in mind, there's a limit to how strong friction can be. And clearly, when I pulled it very fast, I've exceeded that limit. So let's rewrite F of S max as mu Sn. And then, because N is equal to the force of gravity here, which is also written as mg if you want to, we can substitute mg in for N. And what we get is this, mu S mg. And what you saw was that those two weights behaved identical on that particular surface because they have the same value of mu. So our acceleration here, our answer is going to be equal to mu S times g. So what we're going to find is that we can accelerate up to a certain point prior to slipping, and that point depends upon mu. And so it depends upon the roughness of the two surfaces that are interacting with each other. A larger value of mu will allow you to pull it faster prior to slipping, whereas a more smoother surface, it's likely going to slip a lot quicker. So let's say for the sake of argument, if that mu value was, let's say, 0.5, that means that, well, if we're doing our acceleration here, 0.5 times 9.81, we could move this forward at 4.905 meters per second squared. And that would be the largest acceleration we could have prior to slipping. And what you're going to find is that, we can do anything between 0 and this value here. So hypothetically speaking, what if we did just a smaller acceleration? If we had a scenario where my mass is accelerating forward, but only at, let's say, 2 meters per second squared as opposed to 4.905 meters per second squared, what we saw was that it's not going to slip. And what's happening is that you still have your normal force, you still have your gravity, but now you have a smaller force of friction that I'm only going to label F of S instead of F of S max, and those would be the forces in place. So we'd have a lower force of friction, and we haven't exceeded that limit yet. So we can do anything in between. Now, one thing I need to point out here is that when we are moving this, and I'm moving it, let's say, constant velocity after I actually get it to move, while we're moving it at constant velocity, there's no friction in play. It's only while I'm accelerating. So the act of starting the motion and the act of stopping the motion involves acceleration. But while it's moving at constant velocity, we don't require a force to keep it moving. So that force of friction is only present during acceleration and deceleration. And it's actually not going to be a different approach for the deceleration aspect of it. Let's just say, for the sake of argument, we're going to stop moving. That takes time, and that requires the acceleration to be that way, while the velocity is that way. Well, your normal force is still up, your gravity is still down, but now you're going to need a force of friction that's going to be decreasing the velocity over time. So our friction direction will reverse direction when we go to stop it, and there's a limit to that too. Anytime you've been in a car where someone's broken too hard, you might see stuff fly, to the front of the car, because essentially what it's done is it's slipped on the surface. So just looking at this free body diagram, it's kind of indistinguishable from this one, other than the fact that there's direction here. So if I was doing the X direction really quickly, and just recognizing that my force of friction is now to the left as opposed to the right, what I'm going to end up getting is just the same exact solution, just with a negative sign here. Once I put mg in for n, and once again m cancels out, and then there's your solution for deceleration, at least I guess an acceleration to the left here. This is the limit at which we can brake, which you find is will also be 4.905 meters per second squared. So we don't want to speed up beyond that. We don't want to slow down at a rate higher than that in order to prevent slipping.